Okay, let's, I guess, get started. First of all, last week was dynamic programming, which was chapter 11. And how many people, let's just go review, how many people got all four of the problems done? You got all four.
Yeah.
How many people got three of the four? Okay, 2 3s of the fours. Which ones did you miss? What? The turtle one. You didn't get the turtle one. Okay? And how many people got 2? How many people got 1? You didn't get any. Okay. Any particular reason? Was it that like I didn't spend time on it, or these were hard, or I don't understand dynamic programming? Okay. Not enough time. Okay. I encourage you to try to get a couple of those, but those are actually, in terms of lines of program, actually relatively short. Once you understand dynamic programming, my guess would be the problems from last week were pretty short. Does anyone remember how long they are, at least like for the first 2 problems? How long were the first 2 programs? Anybody, how many problems did you get last week? 1. Which one? The first one. How many lines long was your program? 50 something. So these programs are relatively short once you get your mind to it. But there was a debate about a couple of these. Let's maybe quickly go through with it. So you had a complaint that your ferry loading problem didn't work, right? It didn't get past the judge. Right. So how did you do it? What was this problem again? Again, the problem was that we had, I guess we had a boat which had a certain width. We had a length of cars, and we had to assign some to port or starboard each car, so that in the end we put as long a prefix of the line of cars on the boat as possible. That was our problem, right? How did you do it?
I create a binary chart.
Create a binary what?
Chart.
Binary chart. You mean, I think what I'm doing, a Boolean table.
Yes.
Okay.
And to mark whether a certain length will be reached by the first.
Right. So your function was, again, if I'm correct, your function was, let's just pull this thing, I don't know, C of ij was going to be equal to true if and only if the, what was it, first I cars? First I cars could fit in,
not fitting. I mean,
could,
I could choose cars from the first I ones and get it from J.
okay, where there was a length, there was a packing of the first I cars on the ferry. Was it the starboard side or something like that with the port side equal to J? Or what was J equal to?
One side.
With
Either side.
either side. So was J the longest side or the shortest side or the left side?
I mark O and I use the centric variable to recall the logic.
So with J units used on the let's say starboard side. Okay? So the problem really reduces to now finding the recurrence and setting the the initial conditions. I think we set the recurrence last class in a rush, but we didn't really set the initial conditions. And if you're telling me maybe you're having problems, that might be why. Okay, what was the recurrence? Let's try your recurrence. What is the recurrence?
Cij equals Ci minus 1j
Ci minus 1j.
or if j is bigger than the length of I.
Or, wait, this is under what condition? This is as if you can do it, you can get the first I cars so the thing here is that we can put I cars on the ferry with J on the starboard side. If there was a way to do it without the I car, you know, basically, and room for car I on the port side, right?
Yes, but in fact I checked it today.
Well, no, it's got to be, this has got to be, if you're looking at it as a recurrence, this is going to be like a Boolean thing, right? It's a Boolean thing. There is a condition. This is going to be true if this and that is true. Okay? You can't check it at the end, you have to check it now. Okay? Seems to me. Does that make sense? Okay? Or what was the other case?
Because well, just put it this way.
Or what? C sub
0 I minus 1 j minus
I minus 1, and it's j minus the length of car I, right?
Yes.
And here I don't think there is any condition that we need to check, right? Okay? Because in fact, if there is a solution of that type, by definition j is less than or equal to the limit of the car, so this should be good, right? Okay? So I say you have to check this condition at this point, as opposed to checking, I guess you say you want to check it later. I don't see any reason to do that. Okay? Any questions?
I do not quite
Yeah.
understand the recursive formula, but I use a different one.
What?
I use a different one.
What is your recursive formula? Let's go take a look.
That means ij very equals to the maximum right part, the starboard part, left it. Is the ice fitting with first I cars.
Oh, okay.
One of this lens and the starboard is the vortex.
Okay, so what you're trying to say is he's now coming up with let's maybe do this on a different board now, okay, to see what the difference is. You're proposing quite a different recurrence, which might be acceptable, okay? Yours is not a Boolean recurrence, is it?
It's
An integer thing, right? So let's just see what he's saying. He, I think, is saying that C sub I is going to be the max starboard room. Okay, after cars 1 ... to I. that-
I have a J also.
You have a J.
Yeah.
Okay, what is your J?
J is like I have a ferry. It's not an equal length. This length is J and this is.
Wait, no. So let's write this again. So you're telling me. Oh, sorry. So what is your version? Tell me again.
This is IJ
Cij
with the maximum starboard row left it after went to I
Cars.
parts fitting ferry with port part of J length.
Okay, with port length J.
Yeah.
Okay. Now the first question, if we look at this thing, why is this max ever going to be different than the sum of the lengths of the first I cars minus J?
Because J will not totally fitted. I mean not totally.
So with port length, you're saying less than or equal to J?
Maybe that's not equal to J used.
Okay, so
several cars, I mean, not totally fit.
Well, okay. So again, I need to have a definition here. It's kind of important that this be a rigorous definition. Okay? So let's make sure we understand it. You could say, what's the maximum starboard room left? Okay? In a car from 1 to, we have the first I cars, where the port length is less than or equal to J. Is that what you're saying?
Yeah.
Okay, before we were doing it with exact, the difference here seems to be you're letting it be a less than or equal to. And you have a maximum. Okay, that's what you're proposing. Is this right? Don't let me put words into your mouth.
Yes.
Okay? What then is your recurrence? Now, let us think if we believe this is useful. Will this tell us the answer? Suppose we could compute this function. Is this going to be useful to us?
Yes.
Why is it going to be useful to us? What is the answer then going to be? I guess the ultimate answer is going to be, so long as this is positive, you want to know C sub, let's say I, here's the ferry length, right? You want to know what's the largest I such that this thing is going to be positive. Is that right? Okay. And so I kind of agree that if you could compute this thing, that would give you the answer. Okay? But now, can you compute this thing? How do you compute this thing?
It's kind of like that.
Okay?
It's max. It's max. If I put ice in the right part, it will be.
Okay, one different. Okay, try this. Throw that one out. Use this one.
I minus 1. J minus Li. Or C I J minus Li. Of course, this must be larger than 0.
Okay. So let's just take a look at that. You're saying that the largest way to do it is going to be either if we are going to put the car on the starboard side, you're telling me that the room that we're going to have was the room before we put the car minus the car. That's somehow what you're saying, right? And you're telling me that here, if not, you're going to put the car on the other side.
Yeah, on the port side.
And then you want to know,
Oh, I minus 1. I minus 1.
for all the cars, a solution where you had
It's too recursion.
okay, so wait, so let me just say, I'm just looking at this, for some reason it's not hitting in my head as quickly. But this is telling me that either you are putting the car here on the starboard side, in which case you're removing the room. No. Yes, you're putting the car on the starboard side, in which case you remove the room. Or you are putting it on the port side. No, wait, no.
Yes, this
Yes.
is port side.
A port side, in which case you're using that side length. Okay.
And J minus Li must larger or equal to 0.
And here what you need to know is that J minus Li has to be greater than or equal to 0. Okay? So I think that they are equivalent recurrences. Okay? Although I'll admit I think easier in the Boolean way than this way. That's maybe my head in a particular way. And the reason is because, well, wait a second. Actually, for example, let's think whether this is true or not. The thing that I get confused about here is also the less than or equal, just to let you know, okay? It seems a little slippery here, okay? Here you're telling me that you're doing this over all possible solutions with the port length less than or equal to J, right? Now, here you're saying that, okay, let me just think about this. So one thing that's true with dynamic programming is that it's often hard, you have to be convinced your occurrence is right, okay? And this is something that where people make a lot of mistakes people make with dynamic programming because they don't really, aren't certain, their occurrence isn't 100% right. It's a little hard sometimes to see why that is. And so why I get nervous here, although it may very well be right, okay, probably is right, I tend to be much happier when I don't have things like less than or equal here, okay? Because now I have to wonder, are you doing this over all possible configurations right? The maximum starboard row over cars 1 to I when the port length is less than or equal to J. So let's just think whether the less than or equal to is a problem. Because often there's then a max over all other possibilities. Somehow you're trying to say you're avoiding taking a look at all these possibilities by having replaced it with a max. And I'll just say I think I believe this. But this I find slippery. You're saying the judge believed it, so I should trust you. Okay, but I'm just telling you my preconceptions with these kind of things. So in principle, I personally still like my solution better. Although there are probably some deficiency. Actually, no, I would say I like my solution better. Okay? Because it's simpler for me to convince myself that it's right. Your solution isn't that different, right?
Yes.
But my function dip specification to me is easier to understand. Okay? Because I knew it was an exact thing. Okay? And things like less than or equal to or max or something like that tend to get slipperier. Okay? Any questions? I know that's convincing to anybody. And that's just a question of taste. Okay? What are the boundary conditions, though? Let's just figure this thing out. For this recurrence, what were the boundary conditions? What?
0, 0, 0.
You want to say C, 0, 0. Let's just think about it. Oh, wait. We said if we have what's the true if and only if the first I cars on the ferry, okay, have used exactly J units of that. That we would say would be equal to true. I think I believe that. Are there any other cases here that are worth dealing with? Okay. We want to say that
I found the J to be less than or equal to the length of
I think C0 to the length of the ferry is all true.
C0. So, okay, you want to say, okay, so here's the difference between my recurrence and your recurrence is how you initialize it. For this one, you wanted to say that C0 sub I for all I is equal to true. For I less than or equal to the ferry length, which we said was what? Well, let's say F. That's not true for this example, because here I have a definition of exactly, right? For yours, that might be true, okay? But for me, what I would say here is in fact the opposite. I would say that this is going to be false for I not equal to 0, okay? And this would include the negative case, which depending upon how you do it, that might solve your negative case. Some of your room for it things might be solved by negative values. Okay? I think this is the right, enough of a boundary condition. Is that right? Is there any need to worry about the first car? So now what this is going to say, if we start it with 0, with 1, it's always going to go back to 0. And so it's going to get back to, in both cases, it's going to, if I have it completely defined for 0, it will be enough of a basis case. Any questions about that? Okay? Anyway, that's how I would think about it. Okay? Any questions? Okay? Any other issues, dynamic programming one way or another? Okay, so that was chapter 11. I'd like to now go and jump to chapter 13. Actually, usually when I teach this back home, I probably end up slithering into spending a little more time on dynamic programming, but you guys seem to have sort of gotten it, actually. I am going to, usually, there's 14 weeks in a semester. The week I usually don't get to is the week on grids. And I'm pushing that back to next week because we're going to have a substitute that week. Okay, I'm more used to talking about the geometry stuff. So I will talk this week starting about the geometry. Any questions? Okay, so what is geometry? Well, geometry is something everybody here studied in high school, I trust. And I'm even going to trust somehow, based on school systems, you guys may have studied more than most people in American school systems. But what is geometry? Again, in most programming contests have at least one geometry problem. And by geometry here, what I mean are things that deal with points, circles, lines, and so on. We're not going to deal with things that deal so much with polygons here. That's where I'm going to say, I'll call that computational geometry. And we'll do that later. Okay? But here we're dealing with things in real geometry. And programming things with real geometry turns out to be surprisingly complicated for a couple of reasons. I mean, everybody here has seen geometry, you probably know your trigonometry, you know everything like this. On the other hand, what is it that makes programming geometry hard? Okay? So one problem, which is an important thing, is that this issue of degeneracy, which I'll talk about, that one problem is that geometric computations tend to be floating point computations. And floating point computations produce numerical problems. Okay, so that's one-ish complication. What other complications are there with geometry that makes geometry hard to work with? One thing that's related to this we'll talk about is that there's often a lot of special cases that come up, okay, and that you have to deal with for it to be robust. The other thing is that certain things that are seemingly obvious operations on because you're used to doing them by hand or with an eye or by graphics, just somehow require you to do some non-trivial programming to deal with. The idea of elementary operations seem to be harder in geometry. And so we'll go through some of this a little bit. So, again, what I think is the biggest problem is dealing with degenerate. How many people have ever programmed something geometrically? How many people here have done some geometric programming? You're the only one who claims to have done it. And why? In the context of programming problems or anything else?
Some in the context of programming problems and something else.
Something's fun. What kind of fun?
I'm programming a mod for a game.
Game. Okay, so a lot of graphics computations turn out to be geometric things. Okay, and then that's where it comes from.
Not exactly.
Okay, we'll leave it at that. We'll leave it at that then. Okay, so the issue that comes up, if you haven't played with geometric programming, what you find is that in both this and in computational geometry, it is usually very easy to find something that almost works, but a program that will crash when you give it inputs that are special cases. And they call these things degeneracies, the special cases. So, for example, let's take a look at it as a test. When you have two lines, how many points do two lines intersect at? Okay, does anybody know this? Given two lines, how many points do they intersect at?
0, 1, like that.
Okay, the answer that most people immediately will give is 1. Or do they intersect at 1? Okay, the answer is they don't necessarily intersect at all, right? If they're parallel, they don't intersect. And they could intersect at an infinite number of points. How do they do that? Well, they're the same line. So something that is as seemingly as simple as saying find the point of intersection is a messier problem than it sounds. Does that make sense? And you end up getting lots of these, let's say, special cases that come up. And you've got to be able to figure it out. So when we talk about computational geometry, you'll see how I handle some of the, let's say, degenerate cases associated with line segments. But today we're going to talk mostly about continuous things, like lines. Okay, so what is a line? A line is, a straight line, as people say, is the shortest distance between 2 points. But that's really, I guess, a line segment. Okay? What a line is something that passes through 2 points and goes forth infinitely in all beyond that. Okay? I think everybody agrees with that. Now, how would you represent a line? Let's say we have a line in a plane. What are the possible representations for a line in a plane? What? So one representation, which is interesting. Since a line is defined as passing through 2 points, one representation is just to specify a pair of points and say the line is what goes through these 2 points. Does everybody see that? And sometimes that's a good way to represent a point, a line. Why might that be a bad way to represent a line? So, let's think about this. What problems would be hard to solve with lines in the pair of points representation? How would you tell if 2 lines are the same? Okay? One problem is it's not a canonical representation, is that right? So that, this line and this line are the same. But if you're just giving them stored as pairs of points, that would be difficult to test. Is there anything that's easy to do with lines defined by pairs of points? Anyone think of any operation that's easy to do with that representation? There must be. I can't think of one now. But there's got to be one. Okay? Anyone think of anything you can do with lines as pairs of points? Well, how would you judge then if given given 2 lines represented just by pairs of points, how would you tell if they're parallel?
The y-axis,
maybe
in fact,
I'm converting to another.
Oh, okay. So the answer here is that although pairs of points, we agree pairs of points are perfectly good representations. Okay, and that they do describe what a line is. You can't seem to do very much with them, right? So you're saying you want to convert them to another representation. What is your other representation? What does that mean?
So, in fact, for 2 points, you're using define that you get a start point and get a direction vector.
Okay, so another way to do it, you're telling me, is you specify a starting point and a direction vector. Okay? Which you're now telling me is an angle. Is that right?
No.
Okay.
Zero point, but you just specify the direction by that.
Okay. I'm not completely sure I'm yet understanding this, but let's take a look at that. So we agree you could specify a line by one starting point and then the direction vector, which I still think of as being in the plane being an angle. Is it an angle or what is it?
It's like if you previously you got 2 points and you subtract one with another.
Okay.
Direction.
Okay. Why is this a good representation?
Because there are a lot of vector mutations related to that.
Okay. Sorry if I'm seeming dumb, but so what you're trying to tell me is you're taking a look at this instead of before we were taking 2 points. You're suggesting that what you're going to do is instead of representing points A and B, you're going to represent it by point A and then B minus A. Is that what you're saying? Okay. That would be an alternate representation, clearly. Now, why is it more useful? What would be an example of an operation you could do with it?
Test intersection or parallel. Yeah, you just compute the cross product of the two direction vectors.
Okay, so now this may be interesting now. So you're telling me that in order to tell whether two lines are parallel, you're claiming that the cross product rule to tell you that?
Cross product, dot product.
Okay, so if you're good at thinking of vectors, then I can kind of believe that there are certain things like you could tell here. Okay, which are things like again, as you said, whether it is whether things are parallel, whether things are intersecting. Can you compute the point of intersection?
The cross product is not equal to 0 when these 2 points intersect.
Okay, so you're saying the cross product, which just to remind me, so now you've got two lines. Here we've got this, and C, you're saying C minus D. This is what it is. The cross product is going to be, the cross product of, that's XY, right?
Cross product is an area between these 2 vectors.
Okay, we'll talk about area of vectors later on, okay? But I'm still not, okay.
To compute the intersection point, you just give a coefficient for the direction vector for both points, for both lines, and you get an equation.
Okay, tell you what, I'm going to go show you with my okay, this is interesting. I have my own representation, which I'll show you that I like to use. Let's decide whether it's a better or worse than your representation. And when we get up to the operations that I'm going to do on it, let's see how you would do it with your cross product, with your vector representation. Okay? Any other ways that you could think of representing a line? Okay? If you ask my students in school, they would. I know how they would do it. What?
ax plus by plus c is equal to 0.
Okay, so the way the way that my students would do it, just to lead you into the trap, is I'm used to thinking of lines as y equals mx plus b. Okay, where this is the slope and this is the intercept, right? And that is, maybe a little bit like what I was trying to capture here. If we thought of the intercept as being one point on the line, okay, and the slope as being the angle that it's at, okay, that's the usual definition here. What's wrong with the formula y equals mx plus b?
The line parallel with the x-axis.
Right. The problem is that there is one line which it doesn't work for. If you have a vertical line, okay, what is the slope of this line? The slope of a line, okay, m was what was it, delta y over delta x? Is that right? And here when you have a vertical line, delta x is 0, and so they're dividing by 0. Does everybody see that? Now, I guess that doesn't happen with the angle representation, right? But somehow we're used to dealing with it as a slope. So the way that I would represent lines in general is the more general formula, ax plus by plus c equals 0. Okay? This has the property that if we set b equal to 1, then it looks like our normal lines. Okay? But if we set b equals 0, we can capture vertical, these vertical lines, because these vertical lines are of the form x equals something. And so setting a equal to 1 and c equal to something, b equal to 0 and c equals to something, okay, gives us those lines. Okay? So my line type in general is the list of these three, is a structure with these three coefficients. Any questions about that? Now, the one bad thing, what's bad about this well, one, let's say, bad thing about this potentially is that a line, again, is not uniquely defined. Okay? That there is a redundancy here. If I multiply all the coefficients by a constant, okay, if ax plus by plus c equals 0, then 2ax plus 2by plus 2c is also equal to 0. Is that right? So it's no longer a canonical representation. So in principle, testing if two of these things are the same is no longer quite as trivial, unless you fix a canonical representation. And that's sort of what I do in my line type. Okay? I basically make it canonical by insisting that the y coefficient is 1 if it is non-zero, and if y is equal to 0, then I set x equal to 1. Always, okay? And that's basically what this procedure is doing. Any questions about this line type? Okay? And so here I now have a function that takes 0.1, 0.2, and from that builds the three coefficients of the line type. So this does what you wanted to do originally, which is to move between pairs of points of representation and line representation. Any questions about that? Okay. How do we tell if lines intersect? Okay, as we talked about it before, two lines are intersect basically, have one intersection point unless they're parallel. How do you tell if lines are parallel? In my representation now, where you've got lines in the form ax plus by plus c equals 0. How do you tell if these two lines are parallel? Okay? How do you tell if two lines in this format are parallel or not?
First check if b and b prime both equal to 0.
So they're okay, so one argument would be check if b and b prime are both equal to 0. If they,
or you can just check a.
B prime.
Yes, a prime b.
So really what I need to do is to check if a and equals a prime and b equals b prime. I think that's the test that I would use for parallel, for whether they're parallel. Okay? Is it more complicated than that?
Because a equals to 1, b equals to 2, and a prime equals to 2, b prime equals to 4. The two lines are also
Well, the two coefficients are unified.
Right. So the way that I would do it is, I would always adopt the canonical representation. Okay? And in the canonical representation, there are going to be two cases. Either, okay, if it's a normal line, then y is going to be equal to 1. Okay? And then the question is, are the slopes the same? Right? If the slopes are the same, then they're parallel. Okay? The alternative would be that these things are equal to 0. In which case, these things are both going to be equal to 1. Okay? In my canonical representation. And that meant that both of them are vertical lines, excuse me. Okay? So that's how I would do it. Now, how would you do it if they were not canonical? Did you have another? What if these things were not kept in that canonical format?
So then it's a prime b equals
Say a prime b. Is that equal to b prime a? Okay? So a lot of these things become easy if you know enough linear algebra and you have that at your disposal. Okay? My linear algebra happens to be very weak. One of the embarrassing things. Okay? So I would prefer to do it the other way, but if you know these kind of things, this is a good way to do it. Any questions? Okay? Fair enough. Now the other question, though, is if you're doing this kind of comparison, in general, it means you're comparing real numbers together. And part of the problem is that comparing real numbers is a slippery operation. Is that right? So when I do these things, I always compare them not explicitly is it equal to 0, but is it less than or equal to some epsilon, where epsilon is small enough. Does that make sense? Okay, and a lot of things break if you don't do it that way. Okay? Any questions? Suppose, let's say, two lines are not parallel with this format. How do we go and compute the point of intersection? Okay? That's one of the first operations we would want to do. Okay? What? Okay? So the way that you would typically solve it is if we know that these two lines are going to intersect, if they are not parallel, and if they are not identical, then there is one point that is in common. You've got a world where you've got two dimensions, so you've got two unknowns and two equations. The basic way to find the intersection is to basically solve for the unknowns. Okay? Does everyone remember that? Again, how big fresh do people feel about their geometry? Obviously, this is something you learned back in 9th grade. But I will also say that I tend to forget these things over time. Is it possible? How many people feel their geometry is fairly fresh in their head? Good one. How many people feel their geometry has receded into the past? Okay? So that's why I think it's useful to go through these things. Because yes, you did this in high school, and yes, you got through high school. Okay? But on the other hand, it's tough to remember these things, or to remind themselves. Okay. So to solve for the two equations, anything interesting, or does everybody feel they can solve for the equations? If necessary, these are the formulas that you would use for it. But that's basically just algebra at that point. Any questions here? Okay. So when I was writing my program to find an intersection point, what did I do? I got two lines in my three-way point, and I returned it via the point variable. I tested if they were the same line. If so, there is no. All points intersect. Okay, so I just gave them a random one. Okay? I guess in the case of the parallel, in the case of parallel lines, I tested for that error. There were no point of intersection. Otherwise, what I did was do the test explicitly. And it seemed to be that, again, I had to take the special case of, so how do you actually find the intersection? There's the general case, which we solved using these kind of expressions. Okay? And the problem was that they would crash under what condition? Okay? I guess this was the formula for when the lines were, when there was not a horizontal line involved, a vertical line involved, right? This is, I guess, the special case when we eliminate, basically when we knew that b was equal, y was equal to 1 and not 0. Then we had to deal with the special case where b was 0. And then finding, for that case, it ultimately is easy because they were not, because there was only one point of intersection. We knew that at most one of these lines was vertical. And if so, then you knew what y was, what y would be of the, you knew what x would be of the intersection point, and then you would just plug it in for y. So that's, I'm getting to guess how I did it. Right? Is that if this one was a vertical line, then we knew what x was, and we could deal with that problem. Okay? Any questions here? Okay? So that's not so hard. Okay, the other area is, any questions about that? So the other way to think about lines is to think about them somehow as angles, okay? And, an angle is defined as by what they call two rays. But or equivalently, there are angles defined between two lines that intersect. There's a point of intersection, and there are angles around it, okay? How many angles are formed by two lines that intersect in a point? The important point is that there are two, right? They form these four things, but this one is the same as this one, and that one is the same as that one, right? And so one of the tricky things with these things is make sure you know which the right angle is that you're meaning about. But when we measure angles, angles are defined either in radians or degrees. Who here thinks more about angles in terms of radians? Okay, who here thinks about angles more in degrees? Okay, so degrees go from 0 to 360. Okay, radians go from 0 to 2 pi. Which is better? Well, if you can convert between the two of them, it doesn't really make much difference, right? On the other hand, most trigonometric libraries use radians. Okay, so when you do your computations, you should probably make sure that your library uses what your library is using. Usually it uses radians. The other tricky thing about degrees is that occasionally we're used to something like an angle like 57.3 degrees. Okay, right? Now, sometimes angles are given in degrees with decimal representations. And sometimes they're given with degrees and minute representations. Does everybody remember that? Where this is now a number that this number goes from 0 to 360. And this number here goes from 0 to 60. Is that right? So this seems to me to be impossible to work with. Okay? So that's probably why radians, I guess, are a better thing. So you avoid the question completely. Any questions? Okay? So how do we compute the angle formed between two lines? Let's think about that. If I have two lines here, how do we find the angle formed between them? Okay? Any ideas? Think about that. How do we find, if we have a line 1 and a line 2, how do we find that angle between them?
If we have a vector, then the vector of the two lines is.
Okay, so this is one where you're telling me that if you convert this to a vector representation, okay, which was again our point with our offset representation, how now did you compute the angle between them?
Dot product and over their length. If you unify them, then
okay, write that expression down. Okay.
unify what you do.
For the direction vectors A and B, sorry, I'll say it again.
Happy cosine theta.
Anyway, because it's dot product and you got, you know, it should be the sine.
Cosine. Happy cosine. Sine is
Oh.
Okay. So let us remind me of this just so I now know explicitly what we're dealing with here. Okay? So, first of all, you're computing this point. So if I had a line that was represented x1, y1, and x2, y2. The representation of the vector that you're using here is what? x2 minus x1, y2 minus y1? Is that what you're saying?
Yeah.
Okay. That basically people agree with that? And now what you're saying is that the dot product. What is the dot product of two of these points? Okay? Remind me of this now. What is the dot product of A, B, C, D?
AC PD.
I
AC
think that
plus
is
PD.
A, what?
AC plus PD.
AC plus BD. Right. That, okay? Everybody agree that? And you add that up. Right? And you're normalizing this by the distance. What is this dot, this absolute norm that you're talking about?
Length.
That was the length of it. What was that going to be for a given point A, xy? For a given vector AB? Square root of A squared plus B squared. Okay? And this, it says, is going to give us the cosine of which angle? The angle between them?
Yeah. Yeah.
Yes.
Now, how do we know that the angle between them is this and not this?
There's only one because you only have one dimension.
What?
There's
We
only
are
one.
having a vector representation. There's a direction for two vectors. The angle is fixed.
Between
The angle is fixed. So what you tell me is it, and, well, okay, I'm just trying to make sure I'm still understanding this now. So if I gave you two lines,
Because if you use vectors, you are in fact adding extra direction for that line. Because the vector must take one direction on that line.
okay?
can write it.
Square root.
For two lines, you have two. You specify the direction of it. You will have like this. This is the thing. This is the thing. Right. And these two have the same cosine. And the same cosine.
Right.
So
So how would you find this angle?
this angle is
Minus that. Okay, that's fair enough. Okay? Any questions about that? Okay? So that is one way. That if you use the linear algebra, that's the way that you can do it. The way that I would tend to do it, okay, because again my linear algebra isn't very good, is to just note that that there is the following expression that if I have two equations that are in my if I have two equations that are written in my generalized two lines that are specified in the generalized equation, the general form, they will intersect at angle theta given by where the tan of theta is given by this. Okay? And so this is how I would do it. Okay? Any question about it? Okay? The lines that are intersected in the what's it called? Reverse, where I only had, my lines were in general slope intercept format, meaning that it was the non-degenerate lines. Okay? The equation reduced to that. Okay? Any questions? Now, one thing that's useful, well, why is the slope, again, everybody here seems to like this vector representation. Okay? One thing that's a useful concept is that of perpendicular lines. Okay? What does it mean for two lines to be perpendicular to each other? Okay? Their angle is 90 degrees, right? Does everybody see that? How do you test if two lines are perpendicular? Okay? Or how do you create the perpendicular of a line? That's, I guess, how I would. How do you test if two lines are perpendicular? One would be to use this function to compute the angle and see if it's 90 degrees. That would be one way to do it. The other way is to explicitly construct the vector of the perpendicular and test for it, right? How do you find the perpendicular if you have a line of the form y equals mx plus b? What is the equation of the perpendicular line? Change the slope to minus 1 over m. Okay? And that basically does the same trick. Does everybody see that? Okay? So that I claim is also a useful thing. Any questions? Now why this comes in finding the closest point to a line. This turns out to be a useful elementary computation for many things. Suppose, let's say, I give you a line in whatever specification we want, and I give you another point B. How do you find the point on the line that is closest to it? Okay? How do we go about doing that kind of thing? Anyone remember the geometry? How do we find what is the closest point to the point B on that line?
First, just find the slope of the line and then find a perpendicular line connect to it and then find the intersection point.
Right, so the way that I would do it in general is that if we have this line here, we know that if we find the shortest distance between this and this, it's going to define 90 degrees. It's going to define a right angle. Okay? So, of all the, let's say, any point on that line will define an angle. The shortest one is given when it's 90 degrees. Because we can, given the slope of this line, we can now compute what the perpendicular to it is. We know the slope of this line. We now have a line and a slope. I mean, a point and a slope. That is enough representation of this line. The point we want is the point of intersection between the perpendicular and the other one. Does that make sense? So how is it that I found the perpendicular? In here, for the closest point between two lines, I dealt with the special cases of verticals and horizontals, which are sort of a pain in the neck. Okay? But I dealt with them. And then what did I do? I found the representation of the perpendicular line, and then found the intersection point using my previous routine. Okay? Any questions about that? So that turns out to be a useful primitive with these things. Any questions? Okay. The other, let's say, bit of elementary geometry that is helpful is what the basic relations with triangles. Okay? And so what is a triangle? Obviously, it is something that has three angles. Okay? So everybody knows what a triangle is. For computations on triangles, many computations are easier with right triangles. Okay? In particular, what is easy to do with a right triangle? Area. What is the area of a right triangle? It is the height of this times the length times 1/2, right? So if we take this as A, B, C, the area would be 1/2 A times B. So that's one good thing about a triangle, right triangle. What other things can you do with a right triangle? What? Angle. What angle? What aspect of that?
There's a easy angle and one is a right angle. The remaining two one is very easy to find because we can use the triangle side. We can use side to side.
So the claim is that it's easy to find what this angle is. This angle is clearly going to be 90 minus 5, whatever that one is, because it's a right triangle. How do you find out what that angle is?
Outside A over B.
It has to do with what?
The ascending.
This now gets into trigonometry, okay? And in order to use these kind of things, you need to remember what the basic trigonometric relationships are between the cosines of angles and sines of angles and things like that, okay? Any questions? Now, in the United States, there is an old way to remember these things, which I don't know if it's obvious how they do it here, okay? That there is this supposed name of an Indian chief called Soka-Toa, okay? And what was his story, okay? The claim was that the cosine of this angle theta, it was Sa-Toa. The cosine of theta was going to be equal to the opposite angle, the opposite which was A, okay, over the hypotenuse, which was C. Does that make sense? What? No, there's the opposite. For any angle, there is an opposite space. There is a hypotenuse, which is the long end. So this is the opposite one. This is the hypotenuse, and this is the adjacent. Right? Does everybody see that? So the way I always figured, remembered that was opposite was well defined, hypotenuse was well defined, and adjacent was the other one. That was how I always thought of it. Right? Okay, cosine, okay, so how So, let's go back to it, see if I remember. It was so, ka, toa. Does that make sense? Now we believe that. Then the cosine of theta is equal to the adjacent, which in this case would have been B, over the hypotenuse, which would have been C. Any questions? So the good thing about it is that that given a right triangle, it's easy to solve for what the other sides are. Okay? Everybody agree with that? So in order to do this computationally, you need to be able to compute the inverse cosine functions, right? That given a cosine figures out what the angle is from that. But in general, you have libraries for it, a math library for this, right? Does anybody remember how sine functions and arc cosine functions and things like that are implemented? Where do they come from? Okay, there's sort of these magical things that take an angle and compute, or a value and compute an angle from it. Yeah, it's probably some kind of a Taylor series expansion from what you were, when you took calculus, you worried about that. Okay, any questions? Okay, there may be some expansions that are more accurate than others, but that's basically how it actually does it. So the good thing is that for a right triangle, we can solve these things easily. It is less clear that we can solve it or it's a little bit more complicated if it's not a right triangle. But there are laws, if you remember, there are these equations, the law of sines and the law of cosines, that permit us to solve things that are not right triangles, right? The basic story is they were angles, let's say A, I guess in this case it looks like the angles are A, B, and C. The opposing sides, I said, were C, B, and A. The law of sines said that for A over sine A was equal to B over sine B. The law of cosines was a generalization of the Pythagorean theorem, where, again, it said that for any triangle like this thing, it said that A squared plus B squared equals C squared minus this 2bc cosine A term. Okay? Any questions? So why were these useful? The claim was that if you had the law of sines and cosines for any pair of these things, you could compute any set of 3 of these values. You could compute everything else. That was the claim, right? So suppose, let's say I gave you A, C, and let's say C. How would you find all the rest of the quantities of this triangle? Just remember that. Okay? What could we now, how would we go and work out what else was there in the triangle? Certainly, but the law of sines, if we have C angle and C side, A angle and A side, we could get that. Now what else could we figure out? What? Angle B. Why? Because there's 180 degrees in a triangle. That gives us B. And from that now we can work out...
This one's not fixed.
What?
This one's not fixed. You have 2 triangles.
Wait. What was not fixed?
The triangle is not fixed.
Okay. Let's take a look at this.
You have this one. Like this, these 2 of the same length, and this is for the other triangle.
Given that both the angles here, the length of C is small enough,
These 2 are of the same length, so you have 2 triangles.
so that it won't cross.
Wait, no. I gave you 2 angles and a side.
Just a,
I had 2 sides,
you give 2 sides and angle.
and that you're claiming is not enough?
Yeah, because of course this like this way, like this is the same as this length.
Okay. Wait, so let's just take a look. So this was,
One
okay.
C is
So
small
that's 2
enough.
triangles.
side to be dense here. So let's go back here and take a look at the example. So my original example was that I had, well, what was wrong with the reasoning that we gave? Let's think about this. So the reasoning that originally, let's forget about what I had colored here. Let's get rid of all the colors.
The angle should be the angle between these two edges.
This was, I think, A, C, B. Was that it? And here I had A, C, and B. What did I give you?
The HA and C and the
A, what was it?
the HAC and the angle C.
The edge A, which was this, right?
C.
And these two, is that right? Okay. So now you're telling me that there are two triangles like this. Okay?
It's hard to see
Because the C
you
is
can draw C relatively shorter than A.
actually in this way you still have two.
Well,
Take it the opposite, like if you don't color C, you color A, you see this.
okay. Oh wait, okay, so what you're trying to tell me is, let's just think about what this is. You're telling me that I could conceivably tilt, this is the length, wait, no, this is A, this is C. Okay.
The C is the shortest length and the triangle
So now if C is smaller than A,
If C is smaller than A,
yeah,
you're going to tell me it's not set. Okay?
you can draw a.
Okay, someone draw it again. I'm sorry if I'm being dumb. It's been even longer since I've taken geometry than you guys. Okay? Let's take a look.
You have an A, and you can draw a cycle to this. You can see that there are two intersections. It's not true. A cycle.
Sure.
So you can see that this two is the same as, and this two is.
Okay, I see what you're saying here. So in this case here, that is interesting. Okay? Okay. Any questions about that? Okay? So under what conditions is the triangle solvable then? Okay? Let's see if we remember that case.
The
Okay.
two edges with the angle between them.
It's two edges with the angle between them. So given this case, you're telling me that is solvable, right?
And one edge and any two angle.
And so let's just take a look. So, right, with side angle side. Now this is coming back to me, right? The side angle side was the issue, right? Okay? So how do we do side angle? So with side angle side, let's now remember, how would we solve for this triangle? Okay? What was the idea? Okay? How do we solve? What? Law of cosines was going to tell us what the third side was, right? Because we had the angle, we had two of these things, and now we need the third one, right? So with the law of cosines, we would get what that side was. And now how would we work beyond that to find the angles? Now we would use the sine law. Does everybody agree with that? Okay. So side angle side, I remember. What was the other case now? What?
Angle and angle side angle.
Angle, side, angle. Okay? And that was going to be over here.
Any two angles.
Angle, side, B, C. Okay? And why was this going to suffice? From here, I guess we would learn what this angle C was, right? And now the claim was, I guess we could use the law of sines now. Is that right? And fill in those remaining things. Okay? Any questions about it? So, with this stuff, we can in principle solve our triangles. Okay? How do we compute the area of a triangle? In general, there was the, the special case that was easy for right triangles was 1/2 altitude times the base. Okay? Now, that's computing what the altitude and the base is trickier for a, for non-right triangles. Okay? Although this formula still holds. But probably the easier thing to do is to note that there is a linear algebra, determinant way to do it. Okay? That the determinant of, if you take the three vertices of it, AX, X1, Y1, X2, Y2, X3, Y3. Okay? The determinant of this will give you the absolute value of the determinant of this is going to give you twice the area. Okay? Any questions about that? So this is easier. And it turns out to be extensible to higher dimensions. So if you want to compute the volume of something, how would you compute the volume defined by 4 points? That forms a tetrahedra. How do you get the volume of that? It's going to be the same determinant. It's going to be now a 4 by 4 determinant. And the only difference here is that instead of this being 2, this is going to be 6. Okay? This, in fact, is now, this is really d factorial. Okay? So this enables you to compute the volume in higher dimensions. Okay? Any questions about that? The other thing to note, though, is that this determinant can be negative. And so you have to take the absolute value of this. And this is going to be useful to us when we get to computational geometry, actually. Okay? That it turns out that we're going to be able to use this as a way of getting oriented and direction. But so the way that I would compute the signed area of a triangle is just to expand out the determinant formula of that particular matrix. And for the unsigned area, it was going to be the absolute value of that. Any questions about that? Okay, so that's easy. The other basic elementary geometric thing that we have are circles. Okay, and how are circles defined? Usually they are defined in terms of a center and a radius. Okay? So, if you have a center and a radius r, the circle is a collection of points that are all at a distance of r from the center. So the way that we could represent it is as a center and radius representation. That's how I usually represent the circle. Are there any other representations of a circle that people can think of that might be interesting or useful? What's yours? So one possibility is, do 2 points suffice to represent a circle? The answer is no. What?
Except one of this.
So you can squeeze through many circles from this. But it turns out if you have 3 points on the boundary of a circle, that uniquely fixes it. Okay? So that's an alternate representation, but it's not really that interesting. Okay? There's also, I guess, a representation in terms of as an equation. Okay? But computationally, I think center and radius is most interesting. Any questions? How do we compute the tangent line with a circle? Okay? This is one that turns out to be something that we might want to do. Here we've got a circle. Here we've got a point we're interested in. What is the tangent line? The tangent line is the line where we sort of rotated the line around through that point, it would bump against the circle. How do we compute this tangent line? to a circle? Any ideas? Okay, so let me figure that out.
Triangle is another one.
Okay, so first thing to note here is where is it going to hit? If this line has a particular slope, right? What line is it going to intersect at? The answer is the perpendicular to that, right? When it intersects, it's going to form a right angle with that. Is that right? So now where do we go with that observation?
The distance between the points and the radius.
So the claim here is that we know the distance between the 2 points, so we know this length, right? We turn this around, but then we're Pythagoras. This is C, right? The length, the radius here would correspond to like B in this thing. To solve for A, we could use the Pythagorean theorem, right? And now you know what this length is. How do you find the tangent point, or how do you find the line now? That gets us part of the way. Yeah?
I don't think we need to find the length because we can find the angle of this between the slope and the line to the center of the circle. We can find the angle and then we can find.
Okay, so one possibility you can do is you want to try to find this angle. That would be another way you could possibly proceed, right? You know, well actually wait, what is it? We know that, how do we find the angle there? We know what this line is. How do we find that angle?
Because it's
Sine of
right
that
angle
angle.
triangle. Can solve it by 2.
The sine of that angle is the radius over the distance.
I see. Okay. Oh, right. Because we have this is a right triangle. We know that. Right. The sine. We have this. We have this. We have this. We can therefore find this because it's a right triangle. Is that correct? Okay. And that would give you the slope of this line. Is that what you're trying to say?
No need to slope.
What?
No need to slope. Oh.
You want to find this line, a representation for it. Once you had that angle, does that implicitly give you the slope of the line? And you have a point and a slope, that would presumably be enough to tell you that. Is that right? Okay. So that gives you a way to find the tangent. Okay, and that turns out to be useful for several kinds of different problems, including some we may deal with this week. Okay. Any questions? I'd like to quickly review the problems that we're going to go through this week. Then, okay. The first one is one where you have a gopher and a dog, and the dog wants to eat the gopher. And the gopher can hide in a certain number of holes. And the gopher is going to have a strategy to pick its hole. And the dog is going to have its, a strategy of how it's going to run. And the question is there a way to find a safe place for the gopher to hide? Okay? That one's actually pretty easy. The next one says that we want to find the shortest rope between a pair of points. If there's nothing between the pair of points, it's easy. But if the pair of points exist on different sides of a circular pillar, okay, then you've got to somehow calculate what the length of that is. Any questions? The next one describes a cake where you've got 2 children, and the mother wants to describe the cake equally. You might say that, well, if you cut the cake in half, that will do it. But that's not fair because the cake has cherries on top. And they want to make sure that not only do they get equal amounts of cake, they get equal amounts of cherries. Okay? And so the question is, what is the best way to deal with that? And finally, there's a very interesting one about circles, where you're given as input a collection of circles, and you want to sort of put them on a line to minimize the shadow that they shed. So here are a bunch of circles. The shadow that they said would be the width of the narrowest box that would contain it. And the question is, how do you arrange the circles to do that? Any questions? Okay, yes, question.
I never assessed to go through either way or the Photoshop.
Okay, so let's take a look. I've heard rumors that UV programming challenges has been down. Those rumors are true. Is that correct? Okay, I know Miguel's aware of that now. Was the program, was UVA down also?
I can assist you with also.
What are you using to what browser?
Firefox, both Firefox, try both Firefox and ID.
Maybe you should delete the cookies.
Oh, I see.
Okay, so good. Hopefully that'll work, and hopefully we'll get something for next time. Okay, thanks for your attention, and I'll see you guys next time.